Have you ever just stopped and wondered if our universe is some kind of cosmic accident? I mean, it's one of the biggest questions in physics, right? Because all the laws, all the numbers that govern everything, they seem perfectly, almost impossibly set up for us to even be here. Well, what if I told you there's a new theory that says it wasn't an accident at all, but totally inevitable?
This whole mystery has a name: cosmological fine-tuning. Think about it. The fundamental constants of nature, the strength of gravity, the charge of an electron, they all have values that fall into this incredibly narrow range that allows for life. If you nudge them just a tiny, tiny bit, stars wouldn't light up, carbon would never form, and the universe would just be this sterile, empty void. So the big question is, how did we get so unbelievably lucky?
For ages, we basically had two choices on the menu to explain this. First, there's the anthropic principle. The idea here is that there's a huge multiverse with countless other universes, each with different rules. We just happen to live in one of the very few where the rules allow for people to exist and ask the question. The other idea is teleology, or intelligent design, which suggests the constants were set on purpose. But what if there's a third way, one that isn't about chance or purpose, but is grounded in physics itself?
Okay, so before we get to this new idea, let's just make sure we're all on the same page about the problem it's trying to solve.
So cosmological fine-tuning is exactly what it sounds like. This observation that the basic numbers of our universe seem to be just right. I mean, take something like the fine structure constant, which basically sets the strength of electromagnetism. If we're off by just a few percent, poof, no stars making carbon. And without carbon, there's no life as we know it. So the question isn't just that they have these values, it's why. All right, and this is where things get really interesting. A new framework is proposing that our universe's finely tuned state isn't luck at all. It's the destination the cosmos was always rolling towards. It's called the Napierian covariant attractor, or NCA for short, and it's the brainchild of theoretical physicist Jose Lourenço Claudio Junior. He's developed this mathematical framework that doesn't just tackle fine-tuning, but also some really thorny problems in string theory by modeling how the universe's fundamental constants could evolve and settle down over cosmic history. Okay, so here's the absolute key takeaway. The NCA suggests that there's a dynamic process literally baked into the laws of physics that actively guides these parameters to a stable final state. So fine-tuning isn't some preset condition, it's an emergent property. In other words, it's not where the universe started, but where it was always destined to end up. So how can a physical law guide something? It sounds kind of weird, right? Well, there's a really simple and brilliant way to think about this whole idea of an attractor.
Just imagine a raindrop falling anywhere on the slopes of a big valley. It doesn't matter where it lands. That's the initial condition. Gravity, which represents the physical laws, is inevitably going to pull it downhill. And where does it end up? In the lake at the very bottom. That lake is the attractor. It's the stable, final state that the system is drawn to, no matter where it starts. The NCAS is basically saying our universe's constants did the exact same thing.
So, what's really going on under the hood? Well, you can think of it like a cosmic tug-of-war. This is modeled by a surprisingly simple equation, and the key player in it is the natural logarithm, which is also called the Napierian logarithm. That's where the theory gets its name. And this mathematical tug-of-war means there are only two possible outcomes, two places where a parameter could finally come to rest. The first possible resting spot, at a value of about 1.118, is totally unstable. Think of it as balancing a ball on the very peak of a hill. The slightest breeze, and poof, it's gone, rolling away. Physicists call this a repulsor because it actively pushes the system away. It's a state the universe could have been in, but it wouldn't have lasted for a fraction of a second. But the second point, around 35.12, this is the one we care about. This one is incredibly stable. This is our lake at the bottom of the valley. If the system gets nudged away from this value, the dynamics just pull it right back. This is the attractor. According to this theory, this is the natural, inevitable destination for our universe's parameters. They settled here because physics left them no other choice. Okay, that is a really cool story. But what separates a cool story from actual science? It's all about testable predictions. And this is where the NCA gets really exciting. It predicts a very specific fingerprint that we should be able to find in the oldest light in the entire universe.
Here's the idea. The theory says that as the universe's parameters were settling into that stable sweet spot, way back during cosmic inflation, tiny quantum jitters would have created these leftover vibrations. And these vibrations would have literally been imprinted, like a fingerprint, onto the cosmic microwave background, the afterglow of the Big Bang itself.
And the prediction is incredibly specific. Now, don't worry about the math here. The important thing is what it's telling us. This formula basically describes a specific kind of wobble that should be in the CMB data, a wobble that's different from our standard model of cosmology. The two crucial clues we're looking for are beta, which tells us how big the wobble is, and gamma, which tells us its precise shape. So the model predicts the intensity or the amplitude of this finger point. The value of beta is expected to be around 10 to the minus 5. Now that's a tiny, tiny number, is a super subtle effect. But here's the thing, it might just be detectable with the next generation of telescopes we're building. But here's the real kicker. This is the most powerful part of the whole prediction. The shape of this signal, the gamma value, is predicted to be almost exactly 0.5. This isn't some vague ballpark guess, it's a razor-sharp prediction, and that makes it a dead giveaway that could distinguish the NCA from a whole bunch of other theories out there. And what's so cool is that this predicted amplitude, this beta value, isn't just some random number they guessed. No way. It's directly calculated from the other properties of the attractor itself, like its stable value and the quantum fluctuations around it. Everything is all mathematically locked together. And that kind of internal consistency, well, that's the hallmark of a really solid theory. So, there you have it. The theory is on the table, the predictions have been made. So, what's next? Well, now we do what science does best. We go looking for the evidence. We wait for the cosmic verdict. You know, the author of the theory, Jose Lourenço Claudio Junior, said it best. The strength of any physical model comes down to its ability to make predictions that we can actually go out and test. The NCA isn't just giving us an elegant story, it's putting its neck on the line with a hypothesis that could be proven wrong. And in science, that's its greatest strength. And it's not just the one fingerprint. The NCA makes other really bold predictions that actually line up with some deep ideas in string theory. For instance, it predicts that the primordial gravitational waves from the Big Bang should be incredibly faint. It also says that dark energy, the stuff making the universe expand faster and faster, isn't constant, but actually changes over time. And we have a whole fleet of upcoming observatories, missions like CMBS-4, LightBird, and Euclid, that will be powerful enough to test these claims. They're going to be the jury for this theory. So what does this all boil down to? It leaves us with this incredible, tantalizing possibility. The NCEMA isn't just a potential explanation for fine-tuning, it could be a bridge to the ultimate holy grail of physics, a working theory of quantum gravity. Could the answer to why our universe is the way it is, why we are here, be hidden in that faint, ancient glow from the beginning of time, just waiting for us to finally see it?